Assalamu alaikum. Today's lecture we are going to continue talking about the solar system, PV systems. In the previous lecture we talked about the photovoltaic system, part 8. These are the contents, and we talked about the introduction to the PV system, and we talked about the grid connected system and the off-grid PV system, or we call it standalone system. Today we are going to continue section 8.2, behind the meter grid connected systems. In this slide you can see that this is the block diagram of the PV connected grid connected PV system. It consists of photovoltaics, PCU or power conditioning unit, meter, and the grid. In typical PV system that is used for residential applications, the rating of this system will be from 1 to 10 kilowatt. For commercial applications, this amount of power, electric power generated by the PV system, can be increased up to 10 kilowatts or up to 1 or 2 megawatts. So now the question is, what is PCU or power conditioning unit? PCU, actually, it consists of or includes the maximum power point tracker to keep the PVs operating at the most efficient point on their IV curves, as well as an inverter to convert DC to AC. This PCU also includes a DC to AC inverter, a ground fault circuit interrupter or GFCI. The main purpose of the GFCI is to shut down the system if any currents flow to the ground and circuitry, to disconnect the PV system from the grid if utility power is lost. So now we can summarize that the PC unit consists of maximum power point tracker MPPT plus the DC to AC inverter plus a ground fault circuit interrupter GFCI. This is another grid connected PV system, and these are the principal components. So this we can see here: the photovoltaics, the combiner box, the array disconnect, and here is the BC unit. And after the BC unit there is a breaker, and then we go to then you have to go to the load, house loads, or in the other way you have to go to the grid via the utility meter. So most of the cases we are not going to use one inverter for the whole system. So it's better to use micro inverter. So an alternative to having a single MPPT inverter for the entire array, it is better to use micro inverters for each PV module. And here in this diagram you can see that this is a PV module connected to its own MPPT inverter, and there is another PV module connected to its own MPPT inverter, and so on. What are the benefits? What are the benefits of using microinverters compared to using only one inverter? That with each module having its own MPPT, bypass diodes are no longer needed, and the risk of a poorly performing module bringing down an entire string is eliminated. So this is one of the advantages of using microinverters. In addition to having many small inverters will avoid the risk of an inverter malfunction taking down the entire array. This is in addition to the individual inverters also facilitate remote monitoring, which can help identify performance issues module by module, and if a module needs to be replaced, it can be individually shut down and safely removed without affecting the rest of the array. So due to these advantages of the microinverter, so it's better to use microinverters compared to the one inverter in the whole system. In case of large grid connected system, you can use individual inverter for each string like this, or in this case you can use central inverter system to provide three-phase power. In this slide we talk about the net metering and feed-in tariff. Net metering requires no new equipment, since essentially all electricity meters run in either direction. So in this case you have only one meter, and this meter has two directions. So the financial accounting, on the other hand, can be rather complex. For example, in this system, this is an example for the 1 metering system, and in an effort to encourage customers to shift their loads away from big demand times, some offer residential time of use rates, TOU rates. We'll see what is the benefit of using TOU rates in the next slide. So here we can see that this is suppose that this is your day, starting from the morning, noon, afternoon, evening, and this is the distribution of the PV power generated by the photovoltaic system, and its peak during the noon, and this is your consumption of electricity during the whole day. So if you have excess power from the array, you are going to sell this power to the utility, and at night you are going to purchase or buy the power from the utility. This table shows different period of times, morning, afternoon, evening, with the different rates. For morning and evening, they have small rate, while in the afternoon have high rate. And suppose that your PV system delivers this amount of kilowatt hour per month, and suppose your household demand this column, and you can see that the net utility usage with these numbers, when you multiply the net utility usage by the rate, you will get the amount of dollars. But since you have excess power here, you are going to sell this power to the utility, you are gaining money. So you are gaining during the morning, in the whole month you are gaining $17, and during the afternoon you are gaining $27, but in the evening you are paying $20 for your consumption. So the total amount of money you are collecting is $24 credit. So now you are saving money by installing the PV system using TOU tariff. In this system, actually this is another example of the 2-meter system. 2-meter system, we have 2 meters. Each meter has its own tariff, feed-in tariff, one for selling and one for purchase. Yeah. So the sell kilowatt hour, it's different rate than the buy kilowatt hour. And this system can be used to provide separate rates for power generated by PVs and power used by customers. So the next section we'll talk about the predicting performance, how to predict the performance of your PV system and judge if this performance is good enough, or you need to increase it, or it's good, it's better, and it satisfies your needs. First of all, we'll talk about the non-temperature rated or not temperature related PV power rating. PV modules are rated under standard test conditions, or STCs. This standard test condition includes a solar radiance of 1 kilowatt per meter squared, or we call it 1 sun, a cell temperature of 25 degrees, we call it room temperature, and an air mass ratio of 1.5, we call it AM 1.5. So when you are your PV panel is going to be measured under these conditions, so we are going to say this is the standard test condition. So under these laboratory conditions, module output are thus often referred to as watts STC. So the power generated from the PV now, we call it watts STC or peak watts. How to calculate the non-temperature related PV power rating? So a simple way to deal with the goal of converting STC rating into the expected AC power delivered under real field conditions is to introduce a derating factor. So the AC power generated by the PV equals the DC power at STC conditions multiplied by the derate factor. So now the question is, what is the derate factor? What is the value of this derate factor? So this table shows different derate factors for different elements in the PV system, like PV module, inverter and transformer, module mismatch, tie and connections, DC wiring, AC wiring, soiling, system availability, shading, sun tracking, age. Each of them has its own derate factor, and this derate factor, it's within the range, this range. So the overall derate factor can be computed by multiplying all these together. So you'll end up with a total derate factor without temperature impact is 0.77 or 77%. Now we'll talk about the different components in the PV system, like the isolation transformer. So what is the main purpose of using an isolation transformer in the PV system? Is to prevent the fault currents from passing from the DC side of the system onto the AC grid connection. Suppose that this is the PV system and there is a fault, so there is a current is flowing in this way, in this direction, from DC side to AC side. So to prevent this from happening, we have to install isolation transformer in between. So the isolation transformer are going to isolate the DC from the AC circuit and from the grid connection. How it looks like the isolation transformer, it looks like this inside the inverter box. To see how washing the PV panel will affect its generated power, there is an experiment has been done to an array had never been washed before. This example of 20 kilowatt array was producing actually only 12 kilowatt. This why? Because there is a large amount of dust, because it's not washed before. So after washing, the peak output increased by almost 50%. So this experiment shows the effect of washing the PV panel on the amount of collected power. Here we'll see the effect of module mismatch. If you have two different modules and these modules are connected in parallel, for example, and these modules rated with 180 watt both, but due to mismatch, one produces 180 watt at 30 volt and the other one produces 180 watt at 36 volt. So when you connect them together in parallel, you end up with the maximum power of a combined module is only 330 watts instead of 360 watts. So there is a drop in the power due to mismatch. To get rid of this problem, we have to use microinverter in each module. Here is the graphical explanation of what we talked about, the module mismatch. This is the first module and its IV characteristic. This is the second module and its IV characteristic. When you combine them together, you end up with this system with the IV characteristics with the maximum power 330 watt at 30 volts. In the next slide, we'll talk about the shading losses. We know that the shading of one PV panel to another will generate losses. So a design decision must be made between horizontal collectors that can fill the space with no shading versus rows of tilted collectors, which may cause shading from one row to another. So here we'll introduce another factor that is very important for calculating the shading losses. It's called the ground cover ratio, or GCR. GCR is the ratio of the area of the PVs themselves to the total ground area. Smaller GCR, it's very important to note that smaller GCR means the collectors are spaced further apart, so no shading, so the shading is reduced and the rate factor is improved. Let's see this graphically. Here is this figure shows the shading rate factor versus the GCR values, and GCR values changing from 0 to 0.8 for different PV systems. 2-axis tracking, 1-axis tracking, fixed 40 degree, 30 degree, 20 degree, 10 degree tilt. Let's take an example. If we are using a fixed 30 degree tilt and we need a direct shading rate factor of 0.975, so the GCR value should be 0.47. So you have to keep the ground cover ratio to be 0.47 to get this shading rate factor for this photovoltaic system. To clarify this point, we need to go through this example. The cadmium telluride CDTE modules have dimensions of 1 meter by 0.6 meter. So here in this figure you can see the 0.6 meter here and 1 meter in the other way, in the other side. So the area of this PV module 1 times 0.6 meter. Using the shown figure below and the recommended 0.975 rate factor, what should be the collector spacing between rows if the 1 meter dimension is on the top, the 1 meter dimension is on the bottom, and these south facing collectors have a 30 degree tilt angle. So first of all, in order to solve this problem and find the spacing between rows, we need to find the GCR value. GCR, we are going to use this figure to find the GCR value, then we'll go and continue solving the problem. But first of all, I want to mention this table. This table shows examples of PV module performance data, different PV modules with different coming from different manufacturers, and here is our PV module used in the example 1. It's made from the material CDTE, the model number FS series 3, coming from the manufacturer First Solar, and here is different characteristics of the PV panel, like panel efficiency, rated power, rated voltage, rated current, open circuit voltage, open circuit current, NOCT temperature coefficient of power, temperature coefficient of voltage, temperature coefficient of current, and dimensions and the weight. Let's go to the example, back to the example. So to solve this problem, first we need to find GCR, and we mentioned that GCR can be found from the figure, and as we did before, and we found that the GCR value is almost 0.47 to achieve the D rate factor 0.975 for this type of PV panels. So what's the definition of GCR? We mentioned that GCR equals the collector area, we'll call it AC, divided by the total ground area, A total. So the question is, what is the collector area? It's given in the example. It's 1 times 0.6. This is the collector area. Now the question is, what is the total ground area? The total ground area equals the projection of 0.6 meter this side to the ground plane. So it's 0.6 meter cosine 30 degrees. Then we need to add distance d between the two collectors. So 0.6 cosine 30 degrees plus d. This side we need to multiply this by 1. The other dimension that is not shown here in this figure. So once we know GCR, and the only unknown is d, so from this equation we can find d is the spacing between the collectors should be 0.76 meter or 76 centimeter to achieve this shading derate factor as given in this example. Let's go to the section 8.32. We are going to consider the temperature effect. So we are going to discuss the temperature related PV derating. So in this case, we'll study here a very important loss due to cells operating at temperature above the STC reference temperature, which is 25 degrees centigrade. So we call normal operating cell temperature or NOCT, provided by manufacturer, which is based on an assumed irradiation S of 0.8 kilowatt per meter square and an assumed ambient temperature of 20 degrees centigrade. This can be adjusted for actual conditions using this equation. So to calculate the temperature of the cell equals the ambient temperature plus NOCT minus 20 degrees centigrade divided by 0.8 kilowatt per meter square. Then multiplied by S, the irradiance or irradiation S kilowatt per meter square. So if I give you the ambient temperature and NOCT at the irradiation, you can find the temperature of the cell. Now, let's see example 2. Calculations based on Atlanta TMY data indicated that 753 watt per meter square would strike a collector at 52 degree angle, tilt angle, and 20 degree azimuth angle on May 21st at noon. At that time, TMY ambient temperature is 25.6 degrees centigrade. Now, we need to find the temperature derate factor at noon for the single crystal silicon, or it's called SCSI, single crystal silicon module, and from the data sheet NOCT equals 45 degrees and temperature coefficient of power maximum equal minus 0.38 percentage per degree centigrade. So now, how to solve this example? Simply, we are going to use this equation. To find the temperature of the cell, we need to know the ambient temperature. Ambient temperature is given. It's 25.6 degree, and NOCT from data sheet is given 45 degrees minus 20 degree divided by 0.8 multiplied by the irradiation. So the irradiation is given 753 watt per meter square, so S is given. So the only unknown is T cell. So we can find T cell by applying this formula. Let's see. So T cell equals, as we mentioned, 25.6 plus 45 minus 20 over 0.8 multiplied by 0.753, you will end up with 49.1 degrees centigrade. This is the temperature of the cell. So now, temperature, we need to calculate the temperature derate factor. So to find a temperature derate factor, since the temperature coefficient is based on the comparison with the STC cell temperature of 25 degree. So the degradation of power maximum will be, this is the drop or decrease in power, will be 0.38% per 1 degree centigrade. Times, we need to multiply by the difference in temperature between the cell temperature, which is 49.1, subtracted from the STC cell temperature, which is 25 degrees centigrade. So you end up with 9.16 or 9.16%. So this is a decrease in power due to increasing the temperature of the PV module or PV cells. That means 9.2, almost 9.2 decrease in performance. So that translates to a known temperature derate factor of, so what is the NOCT derate factor? It's 1 minus that amount we get from the decrease in power here. So 1 minus 0.016, so this is percentage in percentage, so we need to divide it by 100. So 1 minus 9.16 divided by 100, you end up with 0.908. That means the NOCT derate factor is almost 90.8%. This is end of the example, second example, and here we can see, for more information about this is different TIMI time and insolation, different ambient temperature, different sea temperature, and different NOCT derate factor, and the effective IC. And we can see that in our cases at noon, this is the insolation, this is the temperature, ambient temperature, and this is cell temperature, and this is the derate factor. These are the quantities we calculated from the example 2. In this section, we'll talk about the peak hours approach to estimate the PV performance. So it's very important to talk about the peak hours approach. What is the definition of peak hours? Predicting performance is a matter of combining the characteristics of the major components, the PV array and the power conditioning unit, PCU, with local insolation and temperature data. To see whether this simple approach is reasonable or not, consider the following analysis. We can write the energy delivered in a day's time as, this is the energy delivered per day. So it's kilowatt hour per day equals the insolation. Insolation is kilowatt hour per meter square per day, multiplied by the area, multiplied by the efficiency. So A is the area of the PV array, and eta bar is the average system efficiency over the day, because the system efficiency changes from time to time. So this is the average system efficiency over the day. That when exposed to 1 sun of insolation, we can write the equation again, but in terms of AC power from the system. So the AC power in kilowatt equals 1 kilowatt per meter squared multiplied by the area by the eta 1 sun. What is eta 1 sun? It's the system efficiency at 1 sun. So now we can rewrite the previous equation and write the energy in kilowatt hour per day in terms of the AC power, which is power AC in kilowatt multiplied by the insolation, kilowatt hour per meter square per day over 1 kilowatt hour per meter square multiplied by the eta power over eta 1 sun. So if we assume that the average efficiency of the system over the day's time is the same as the efficiency when it is exposed to the 1 sun, then eta power here equals eta 1 sun, so this will cancel out. Then we end up with the energy per day equals the AC power times the H over D of peak sun. So an estimate annual energy production from a PV array will be, we need to calculate the estimate annual energy production. So the energy per year, it's kilowatt hour per year. It will be the power DC at STC conditions times the D rate factor times H over D of the peak sun multiplied by the number of days per year, which is 365 days per year. And this term actually the annual insolation. Okay, let's take an example 3, and this will show you how to use these equations. A house facing 5 kilowatt DC at STC conditions, array in Atlanta, has a tilt angle equal 18.65 at latitude of 15 degree, for which BV watts estimates the annual insolation of 5.12 kilowatt hour per meter square per day. So by the way, BV watts, this is a software program or online calculator. You can use it in this example. Using the first part of this example, using the peak hour approach, estimate the annual energy that will be delivered. This is a relatively warm climate area, so let us assume an overall rate factor of 0.72. There is different requirements in this example, but let's focus on the first part, how to solve this part using the peak hour approach. So we need to use the formula to find the annual energy estimated can be delivered from this BV band. But first of all, I'll give you a quick hint about the BV watts. BV watts, actually, when you go to online and you look for the BV watts calculator, you will see this this web page. And to get started, you need to enter your location of a home or business address. Once you enter your location, it will give you all different calculations, as we'll see later on. So the first part of this question or this example, so we need to use here again the per peak hour approach. So peak hour approach, we are going to use this formula to calculate the estimate annual energy production. So the energy in kilowatt hour per year, it's BDSTC times the D rate factor times H over D of the peak sun multiplied by 365 days per year. So now the question is, what about the BDSTC? It's given in the example. Go back. This is a BDSTC. So it's 5 kilowatt. What is the D rate factor? It's given in the example also. It's 0.72. So H over D of the peak sun, it's given also in the example 5.12 here it's 5.12 kilowatt per hour per meter square per day. This is the annual insolation. So we have to put this, and then multiply by this. You end up with 6727 kilowatt hour per year. This is the annual assumption of energy production. Go back to the online calculator, the BV watts calculator. When you enter the location, as in our example, you will get the resource data. Resource data will give you the latitude and longitude of your location and the map. Then when you go to the next part of this calculator, you will see system info. System info, you enter the DC, system size, the power DC, the module type, the array type, the losses, the tilt angle, the azimuth. I entered all these values as given in the example. Then you go to the results. Once you go to the results, you will see the annual energy production. So S6 almost 6,622, and let's go back to our example. It was 6,727. So it's almost similar or very close to each other, and it gives you the total annual production, and in each month by month, and this is a summation or the annual production. So it's very important to go online and use this calculator to solve your example. Let's go back to the second part of this question. Then use the PV Watts online calculator. So we are going to use this PV Watt online calculator to compare the results. Okay, like what I did exactly before. From these results, determine the value of the overall annual D-rate factor that works in the equation, with 0.77 being the default non-thermal D-rate factor. What would be the D-rate factor for the thermal or the temperature alone? Okay, so let's go back to the PV Watts online calculator and see what will be the amount we get from the calculator. We get almost 6,624 kilowatt hour per year. Suppose that the D-rate factor, the overall D-rate factor is 0.77 without temperature. Okay, without temperature. So how to calculate the overall D-rate factor with temperature? So what you are going to do is to divide this annual D-rate, energy production by the calculated value from the peak hour approach, PDSTC, multiply the overall D-rate, multiplied by the number of days per year, so you end up with 0.709. So what is this number? 0.709. This is the total or overall D-rate. If you know that the D-rate factor without temperature 0.77, so what will be the D-rate factor for the temperature? So the temperature D-rate will be the overall D-rate divided by the D-rate factor without temperature. So we have to divide 0.709 by 0.77. So you get 0.921 or 92%. This is the D-rate factor of the temperature. Okay, so this is the end of this example. And here in this this table shows different D-rate factor, as we mentioned before, for different systems or different sections or parts of the system. These are the different D-rate factor and the overall D-rate factor, as we mentioned before. Let's go to the last part of this question. Part C. What improvement would be realized if modules had microinverters that eliminate the module mismatch D-rate, and which is also replace the PV Watts 20% D-rate DC wiring losses with 1% AC wiring losses? Okay, so how to solve this? We have to go back to this table, and we see all different D-rate factors. He says that suppose there is no module mismatch anymore. So instead of 2% losses, it becomes no losses. That means the D-rate factor becomes 1. And also he said that the DC, suppose that DC wiring 2% loss becomes 1% loss. That means the D-rate factor instead of 0.98 becomes 0.99. Then we need to calculate the new PV Watts D rating for all of them. So we need to multiply all of them, but we have to consider the two new numbers here. So we end up with a new number 0.798. This is including the module, there is no module mismatch, and the DC wiring D rating losses becomes 1%. So when you multiply all these together, you get 0.798. Then the total D rate becomes the multiplication of 0.798 by the temperature D rate. You get the overall D rate factor, and then the energy will be from the peak hour approach 5 multiplied by this D rate factor, the new D rate factor, multiplied by 5.12 times 365. You will get 6838 kilowatt hour per year. This is the energy estimate of energy production. So there is a post of 214 kilowatt hour per year when we are improving the module mismatch and DC wiring losses. The last section we'll talk about the normalized energy production estimate. With the online calculators readily available, we can easily derive performance data for different PV technologies in different locations. One handy way to make such comparisons is by using manufacturer provided BDSTC rating to normalize the predicted kilowatt hour per year system output. For example, in the next figure shows the normalized output for 5 collectors that we have been using for examples. These are the normalized output by different PV technologies for the modules at Palo Alto, California, tilt angle 38 degrees, 94.5 degree percentage efficient inverter using this CSI calculator. We can see that the best performance is for CDTE or cadmium telluride, and then the ASCI or amorphous silicon, and then different types of modules. And to calculate the power losses for each type, this is the equation for SCC silicon or MSC silicon or CDTE or CIGS or AA silicon. For each one, these are the losses equation. Then in this section we'll talk about the capacity factor for PV grid connected system. A simple way to present the energy delivered by any electric power generation system is in terms of its rated AC power PAC and its capacity factor. So we can define the energy per year in terms of the power AC PAC in kilowatt times the CF, which is a capacity factor, multiplied by 8760 hour per year, and 8760 is the product of 24 hour a day multiplied by 365 day per year. Then we can formulate the energy per year in terms of the power DC STC multiplied by the SCF DC multiplied by C 8760, like from this equation, and combining these together we'll end up with the energy production per year BD multiplied by D rate multiplied by H over D multiplied by 365 days. So we end up with the definition of the capacity factor, DC capacity factor, H over D of the big sun divided by 24 H over D multiplied by the rate factor. So we can use this actually DC capacity factor to define the performance of the system. Some practical design consideration in the last section. Actually, it's given the PV system we need to supply 5,000 kilowatt hour per year to a home in Silicon Valley. Do calculation by hand, making assumption as needed. Test the final design using the CSI or California Solar Initiative Incentive Calculator. Use the zip code 94305. So this is an example for the CSI calculator. You can go through it online and see how to use it to solve this problem. And this problem actually has been discussed in this example or here in this slide, but we are not going to focus on this example. Yani we'll stop here at this part